Long before satellites, climate models, or even thermometers, humans tried to understand why some lands froze, while others baked under the sun. This is the story of how we turned centuries of questions into a system that shapes how we live today. Throughout history, humans have tried to make sense of the forces that shape the world around them, the winds that howl across deserts, the rains that feed the forests, the cold that locks the tundra in ice. And yet, as we look out at a planet full of climate diversity, how do we begin to organize it? How do we categorize the invisible rhythms of the atmosphere into something we can actually use? Imagine you're handed a dataset of 500 cities worldwide, and asked to classify them based on their climates. Would you group Reykjavik and Bangkok together? Or Vancouver and Dubai? Clearly not. These cities experience vastly different atmospheric regimes, ranging from subarctic to tropical monsoon to hot desert. So how do we construct meaningful categories in such a complex system? How do we systematically classify global climates, and what criteria should we use? Welcome to an exploration of climatic classification, a fundamental process in climatology, rooted in both logic and data science. Climate is more than just weather. It's the sum of atmospheric behavior over time, measured not in hours, but in decades. Temperature, precipitation, humidity, wind, cloud cover. Each of these variables tells a part of the story. But the weight assigned to each depends on the purpose of the classification. Are you looking to build wind farms? Then wind speed and direction are what matter. Are you studying agriculture? Then it's rainfall, evapotranspiration, and temperature extremes. The way we classify climate isn't fixed. It's a tool. And like any tool, it adapts to purpose. Climatic classifications are inherently goal-dependent. They're constructed not only from data, but also from intent. The urge to classify climate is ancient. As early as 500 BCE, the Greek philosopher Parmenides proposed a logical framework: 3 zones, Frigid, Temperate, and Torrid, mapped along lines of latitude. This was an early logic-based classification, conceptual rather than empirical. Later, Hipparchus refined the idea using solar angles to define these zones, calling them climata, meaning slope, referring to the sun's inclination across Earth's surface. They didn't have thermometers or barometers, but they had reason. And it wouldn't be until the invention of instruments, like Galileo's thermoscope in 1593, the thermometer in 1612, and Torricelli's barometer in 1643, that climate could be measured with precision. Fast forward to the modern era. Across the globe, tens of thousands of weather stations continuously monitor and report meteorological data. These data streams are collected by national meteorological services, compiled by global climate databases, and analyzed by atmospheric scientists. But, why classify all this information? Because it gives us power. We can forecast the general weather trends for a place across seasons. We can identify climatic normals and extremes, useful benchmarks, even where local data is missing. And over time, we can track how these climate regions shift. Signals of change that affect crops, ecosystems, disease spread, and human health. By simplifying the overwhelming complexity of weather data into spatial and temporal patterns, climatic classifications help bridge the gap between observation and application, transforming raw numbers into actionable geographic intelligence. An effective classifications must do 2 things well: minimize variability within each category, and maximize the difference between them. Too many categories. It becomes unmanageable. Too few. And you're lumping together environments that behave very differently. Classification is the bridge between raw data and real-world insight. In that sense, climatology joins a long tradition. Biologists group life into kingdoms and species. Geologists sort rocks and minerals. Chemists arrange elements into periodic families. Classification is a universal scientific instinct, a way to tame complexity. And yet, climate is perhaps the most dynamic of all. Now, let us look at the most famous system. That would be the Köppen climatic classification, introduced by botanist Vladimir Köppen in the 1870s. Simple yet powerful, it uses monthly temperature and precipitation data to divide the world into zones, each closely aligned with vegetation and soil types. But for more precision, especially where water balance is important, scientists turn to the Thornthwaite classification, developed in 1931 and revised in 1948. It accounts not just for moisture and temperature, but for actual water availability, integrating the interaction between precipitation and evapotranspiration. Köppen offers a broad picture, whereas Thornthwaite delivers hydrologically relevant insights. Each has its role, depending on what you're trying to understand. From the logic of ancient philosophers, to the data of modern science, our understanding of climate has come a long way. And yet, classification remains our most powerful lens, a way to see patterns in the chaos, to translate numbers into knowledge. Climate is complex. But classification gives us a map. A map of how our world breathes.
Please like, share and subscribe to Earth Diary to see more such videos.